course, so in this context, it's basically a basaltic crust. And so, of course, this work is being done in collaboration with Xuzhang. So actually, he also visited Kaukazistan a few years ago in ERI. And of course, my colleague Lars and Charlie at UCL. And sorry about that. So basically, I want to basically address a few things is of the main interest of this talk. And first, so basically, we want to understand the mantle composition, and especially focus on the transition zone. And second, we want to understand the degree of hydration in the transition zone, especially close to the stagnant slab. And as you can see in the background of the last slide, so it's not very clear over here, but you actually see a very clear image of the stagnant slab near eastern part of China. So a lot of study has been linked to how much water has been transported through subduction zone that's stored in the transition zone. And the third question we want to hopefully to address is what's the consequence of mechanical mixing? So of course the Earth is a dynamic system. So what you imagine is of course not necessarily a homogeneous composition. So the background here we show a parallite. So a relatively standard mantle composition that discussed by the petrologists and the mineral physics. But of course, as we know from another study, including geochemical and seismic analysis, mantle is not homogeneous. And so most often, after a few billion years of severe subduction, convection, and severe stirring in the mantle, maybe we are looking at something like this, where a lot of heterogeneities reside in the mantle. So what you see here, the red color basically indicates the presence of basalt. As you can see, in this particular figure, it just shows the density of the basalt is much larger than the ambient mantle. So in this case, it sinks down to the core-mantle boundary. So to focus on the mantle transition, so this is just some of the standard model. So basically from first 2008, it shows the composition and the mineralogy as a function of depth from surface to down to 1,000 kilometers. And basically we show the upper mantle is basically constituted of olivine and also as well as other secondary minerals. And typically in the context of parallite, about 55 to 60% of olivine. And of course, as the pressure and temperature increases and you have change of mineral phases from olivine to their high pressure phase such as waterline and ringotite, and also lower mantle phase as well after you cross the 670 kilometers. And of course, the transition not just happened in the olivine system, but also happened in the garnet system. But in any case, if you look at the seismic property associated with parallite, so on the right, you can see basically the seismic profile as a function of depth. And you can see basically two different systems. So the solid line indicate the velocity and the density profile for oceanic crust, and the dotted line show the property associated with the Harzburgite. And as we all know, that the morph is basically a representation of oceanic crust, and this is the depleted part of the melting, which is the Harzburgite. So most of the signal associated with the transition zone seismic discontinuities are basically corresponding to the component associated with the Harzburgite, because basically a lot of olivine are stable over that pressure and temperature range. So if Earth is very simple, so this is basically what we would predict how the seismic velocity profile look like in the transition zone. So again, what you see here is the Vs density as well as the Vp as a function of depth. So if you look at the magnitude of this velocity jump as well as the density jump, so typically it's about 7% for Vs and 3.6% for density. And so in terms of a parallite, in this particular calculation, you can mix up about typically 80% of hard-to-guide plus 20% of more, which is equivalent to a parallel composition. But I guess the story is not so simple. So as pointed out by Bass and Anderson many years ago, so when you try to compare seismic observations with mineral physics prediction, so what happened is this velocity jump is usually too small. And so what you see here is the solid line shows the prediction according to the olivine phase. But the dashed line shows the observation. So for BS as well as the VP. So it's clear that the observed jump is much smaller. So this is some of the question has been discussed over the past several decades, in fact. And of course, on the right, you see some of the earlier models proposed by Don Anderson, which suggests maybe actually in the transition zone, a lot more ecogite or much less olivine in the upper mantle. And so in this case, as we discussed, the jump is much smaller than the prediction from related composition. But of course, as we know, the Earth is dynamic. So what happens is we have a long-term mixing in the mantle over billions of years. And here just show an example of what happens when you have a severe convection over such a long time scale. We basically can observe in the calculation, which is done by Kagala and also Baumer et al. What you see here is the basalt fraction as a function of depth. And as you can see in the previous plot, a lot of basalt accumulate at the bottom near the communal boundary. But actually, depends on the model. Sometimes you see accumulation of much more basalt in the transition zone as well. And what we can actually see is this actually depends on a particular setting in the geodynamic model. And as you can expect, the density profile and the difference between hard-to-guide component and the Moore component will actually dictate how you actually accumulate the basalt over a geological time. And here just to show another example with the different thermodynamic parameterizations, the density profile is quite different, which end up giving a different prediction of the basalt stratification. And not just long-term mixing, there are probably a short-term mixing as well. So here basically show an example by Baumer et al. In 2013, which focused on the mantle flow near Hawaii. So what happened is in their simulations, they also consider two different components, the peridotite as well as the ecogite. So as you can see, the density difference between the two is quite large. And what happened is depends on, of course, the temperature inside the plume. They often actually observe this accumulation of a large amount of basalt near the transition zone depth, especially above, right above the transition zone. So perhaps what we try to discuss, maybe this difference in terms of the prediction between mineral physics and observation by seismology is related to this mixing ratio, how that's stratified over depths. So of course there are alternative hypotheses, right? So here basically a cartoon shown by Corrado in 2011. So what happened is consider this long-term mantle convection. There are two scenarios. So one possibility is the presence of a lot more water in the transition zone. So in this case, it's 0.1 weight percent scale. The bottom, what you can see here is maybe in the transition zone is relatively dry, but there's an accumulation of a lot more basalt or recycled crust over a geological time. So of course, the main approach in this study is trying to link the mantle convection and how the stratification of mantle rigidity influence mantle convection. So in this case, we use approach combined seismology observation as well as mineral physics prediction. So of course, many people try to observe seismic properties of seismic discontinuity near transition zone. So there are a few things we really want to understand. So we want to know how much is the jump, both the velocity as well as the density jump. We want to know how sharp is the jump, and we want to know the gradient above and below. So in this way, basically, we have a full characterization exactly what the transition looks like. And so before I introduce our approach, so I want to basically summarize what has been done so we have some perspective. So here basically we are looking at a lot of approaches done by a lot of people. They focus on the reflection of this seismic discontinuities. And as you can see, in this case, they can look at the long period SS wave, so which spawns at the surface and recorded by the station. So what happened is this is typically a relatively long period wave, about 10 to 25 seconds. And the problem of using reflection or limitation is very difficult to retrieve and constrain the density jump and the velocity jump independently. So basically here show example by Peter Shear and colleague. So you can have an estimate on the impedance, but there's a strong trade-off between the density jump and velocity jump. So this is one of the main limitations that people try to overcome. And of course, we are not just looking at long period wave, but we can also look at high frequency wave. In this case, we can look at the PKP precursors. So in this case, the P wave traveled through the outer core and also bounced on the other side and recorded by the station on this side. So what happened is once you encounter the discontinuities, and you can basically have a reflection as well. But typically this phase is complicated, but also a high frequency as well. And again, the problem is this phase also resolves reflectivity and does not have a dependent constraint on the density as well as velocity jump. And so how can we resolve this? So people have think about different ways. And here shows, again, the trade-off between a density jump and the velocity jump estimate. And one way we can retrieve independent information is to add additional observation. So in this case, people consider to use the conversion that converted at the boundary and recorded at the station. So in this case, those conversion only dependent on the velocity jump. So what happened is when you combine multiple observations together, the trade-off is much less. And of course, this is still depend on the quality of the observation, which I influence exactly how well is your final estimate. So in this case, if we combine two different data sets, we can reduce the trade-off. Of course, in this case, there's some problem regarding to the sampling inconsistency. So what happened is those SDS or SS reflections have a very wide Fresnel zone, which means the sampling area between the two phases is quite different. So basically, we are sometimes compare apple with oranges. Then, of course, in this case, it's still very difficult to characterize a sharp feature with a gradient zone because this kind of observation are concentrated at a long period, about 10 seconds. And of course, there are also approaches to try to combine seismology with neurophysics. So in this particular case, by Camarela 2009, using the long period seismic wave. So they test a few different possibilities. As we showed earlier, so basically here shows the basalt fraction as a function of depth. So we have basically three different possibilities. A constant basalt fraction about 0.2 or 20%, and maybe 40%, and also in this case, the C2 model indicate accumulation of basalt only in transition zone. And their result actually is very interesting. So what happened is they could not really tell the difference between case 1, a constant basalt fraction with an adiabatic temperature of the steps, versus case 2. So in that case, there's an accumulation of basalt, but in this case, it's a sub-adiabatic. So what happened is there's a trade-off between the temperature as well as the composition. And so this is really the limit in this kind of approach, where the observation was basically adapted at relatively long period. So what we need is actually require a short period analysis. And so in this case, we have to basically analyze the wave much shorter than 15 seconds. And to focus on this study, So again, so this is the parameter that we try to understand, and this is going to be the observation we try to utilize to retrieve this information. So we will basically use the conversion from the boundary. We will use topside reflection from the boundary as well as the frequency-dependent amplitude over a wide frequency range. In particular, we focus on from 1 second to 15 seconds. So in that case, that gives you enough resolution over the detail that we want to understand. And of course, in this case, then we will utilize the prediction as provided by Manifesto, and we will actually compare the observation against prediction. And of course, in this particular context, we can estimate the result fraction, but this observation is not limited. So if you have a different consideration of what sort of a composition that may be more appropriate in the mental transition zone, you can still use this kind of data to constrain your model. So I want to basically show some geometry. So we will basically use the receiver function conversion and topside reflection, and the definition of receiver function that I will introduce a little bit more later on. But as you can see, for any given source that recorded by that transmit a seismic wave through the station, there are a few waves that we are particularly interested in. So one is this conversion wave. So in that case, it's coming from the source and convert at the boundary and record at the station. And of course, there are some other topside reflection. But if you zoom in this bounce point and conversion point, the nice thing about this particular approach is they're basically at the same place. So this is the scale bar of 10 kilometers. So that means we'll compare apple with apple. Then the constraint is really self-consistent, and the sampling region is exactly the same, which is different from other observations. So we have some advantage in terms of consistent sampling. We have a bandwidth that is suitable to resolve the detail. Then we are able to minimize the trade-off between the velocity jump as well as the density jump. So what's the property of these two different waves? So we have is a topside reflection, either PSS or PPS. We also have a conversion from the boundary. So basically here, show a few plots that display the amplitude as a function of transition width. So how sharp is the transition? As you can see, for this conversion, the amplitude drop relatively slowly over about 10 kilometers. So which means if you have a relatively smooth transition, the amplitude becomes small. But what happens is when you look at this reflection from the top, then their decay is much faster. So in other words, they are even more sensitive to sharp or smooth boundary. So to combine both these observations basically give you a much higher resolution on the sharpness of the boundary. So now I was thinking that typically I don't speak too much on the method, but I thought maybe in this context I want to say a bit more. So what we really want to see is some conversion or scattering that happen in some boundary in the interior of the Earth. So in this case, on the left, we show a cartoon that displays the wave of the incoming P wave that scattered at some boundary and reported by the station. And so you have the main P wave. Also, you have a lot of Kaga or other scatter wave. And usually, this kind of a scatter wave is small. So if the P wave amplitude is 1, there are maybe 1%, maybe 2%. So in other words, it's quite difficult to retrieve useful information that you can use to constrain. So this particular method, or that commonly used, really try to take advantage of the analysis of the data. And so basically we try to tease out very small signal that embedded in the noise and also in the source complexity. So what happened is earthquake is not an impulse. So earthquake has a time history. So what happened is different earth has different history. Then in that case, you could not really unify and equalize the response that localized the property of the boundary. So here just to show an old plot, which shows the event in the 60s. And as you can see, this is quite old. And basically what I display here is the P waveform at different component, vertical, north, east, and other direction for maybe 4 different earthquakes. But they are recorded at the same station, but as you can see, they look quite different. So what happened is the source characteristic is so different between different earthquakes. So there's almost no way that you can uniquely retrieve information that you care about, which is the property of the boundary. So how to take advantage of the data, because we still have this vast amount of the data, but how can we retrieve those information that we need, despite it's quite small? And just to orient yourself, so here is the source-receiver geometry. So between the source and the receiver, and of course, here we basically, of course, have the geographic coordinate, but we also have the rate coordinate. So in that case, from earthquake to the receiver, this is the R component, and this is the T component, 90 degrees from R component. And so if you look at the signal that we are looking at, so you have the main wave, which is the P wave. You also have a small complicated coda. And so what happened is, in this case, we are actually able to retrieve those information by taking advantage of the data. So if you look at this spectrum waveform in the spectrum domain, so here's the imaginary part, here's the real part. So this is the main P wave, direct wave. This is the scattering wave. As you can see, it can come from different amplitude and also different phase. And the entire seismogram is a dimension of the P wave as well as the scattering wave. So if you have the displacement waveform at those different components, so vertical, radial, and transverse, and those displacement waveform typically involve the instrument response of what the sensor you are using to record the seismogram. And also there's a source response. So in other words, earthquake has history, but in addition, there are also response between a seismic wave and the structure near the source. So this is also that embedded in this particular source chunk. And then you have the median response, which is E at different component. So this basically make up the seismogram at the vertical, radial, and transverse. So the problem is, how do we actually get this response at the radial and transverse component, which have the scattering information you need? And of course, we can always look at this in not only in time domain, but also in the frequency domain. It's just a multiplication, which is simple. So of course, if you want to get the response, so you got your displacement waveform. If you remove the instrument response, and if you know the source response perfectly, then you got this without problem. But the problem is we don't know. So that's really difficult. And so people think about how to better estimate the source property, but still there's a limit, right? So how well you can understand estimate frequency band. So in this case, this is not the known, and that's a problem where we have a difficulty to retrieve the median response, in this case, ER. And so what happened is people think about different ways. So motivated by this scattering amplitude at the low incidence angle, as you can see, the distance between the source and receiver is quite long. And so the scattering amplitude is quite small. As I mentioned, maybe 8%, less than 5% or so. And one thing you can actually do is, so I remember the workshop of the last week, so we always talk about the homogenization and how important is the epsilon, which has to be small for the method to work well. Here is the same, right? So if you consider the vertical response as the P wave plus some scattering wave, and if the scattering wave is very, very small, so what happens is you can approximate this vertical response approximately equal to 1. So if this is very small, this is approximation. Then the vertical response in the frequency domain becomes approximately equal to the instrument response plus the source response. So as you can see, this is only an approximation, but it shows that if this scattering wave is very small, this works well. So in that case, what you can do is you want to retrieve the response in the radial component, then you have your displacement. Because of this approximation, then what you actually do is to divide the radial component by the vertical component. So this is actually the essence of the method. And the point is, this only works when the scattering amplitude is small, as you can see in previous analysis. So you have basically two examples. So on the left, showing the synthetics, the vertical component, the radial component displacement. then you can basically do the deconvolution, then this is what you get. So this you can identify those conversion wave as well as the reflection wave. Here basically show the seismic observation at a particular location and with a different model, and again, that this is what you can get. So as you can see, there's some difference between the impulse response, which is the green function, and also in this case, the receiver function. So as we are interested in the conversion as well as the topside reflection. So on the left, you can see which is a calculation of the exact green function at different components. So you have the P wave, you also have some other multiples in the vertical component or the radial component. Here basically show the receiver function. And as you can see, so in our case, because we do this deconvolution analysis, what happened is the receiver function, the P wave is basically on order of 1. And those scattering waves are typically on the order of epsilon. So in that case, it's quite small. So basically, we are accurate up to that scale. So of course, if we consider arrows, which is the order of epsilon squared. So in other words, if the scattering is very small, of 1%, then this is really, really small. So this is a good approximation. And the point is, this allows us to retrieve information so they are can be analyzed. Otherwise, it becomes very difficult. But of course, when you do those deconvolution or division in the spectrum domain, that really depends on the level of the noise. So again, so in this case, it shows the wave for a low signal to noise ratio, and here it shows the wave in high signal to noise ratio. So as you can see, the phase division that may be caused by the presence of noise is relatively limited, so the deconvolution may work quite well. But in other case, when the noise is large, then the deconvolution may become not very stable. So what, of course, you can do is do some normalization, or in this case, we can put some sort of water level. So in that case, when you divide it, you can actually give some constant. So in this particular case, we call a water level constant. So what this actually do is to basically remove the spectrum hole. So when you divide it, so if the denominator is very small, then the result becomes very unstable. But of course, once you introduce this particular constant or damping in terms of the inversion, then you got something relatively smooth. So you cannot get all the high frequency that you would like to. So of course, in this case, this is actually the receiver function, which you will see later on. And of course, in terms of this particular water level constant, it's really related to the damping constant that you typically use in inversion. Of course, this is a very simple case. The spirit is actually quite the same. So now, of course, just to finalize in terms of the coordinate system. So you have, of course, the vertical and radial and transverse that in our board. Then to be more clear and convenient, we use the ray-based coordinate system. So in other words, we use the L, Q, and T. So in that case, this L component is exactly parallel to the incoming P wave. Then this Q component is 90 degrees from that. So just a simple case that so you can understand exactly how things work. So in this case, we basically show us low velocity layer that embedded in a high velocity half space. You have an incoming wave coming from the left. Then you can basically see, depends on the angle, which is defined by the ray parameters. So you have all the P wave, which you can align. Then you can basically see the conversion from the top and the bottom of the boundary. As you can see, they actually do not really arrive at the same time, but they follow some slope, which is the slope. Then, of course, you can take advantage of the slope. Then you can stack over, and this is what you get after you stack over a wide range of observation at different angle, which correspond to different epicentral distance. So again, so what we can actually do is do something very simple. So of course, we have a reference distance, which is determined by the P naught, which is the reference rate parameters. And also you have the time shift between the conversion and also the P wave. So what happened is there is always some difference in the timing, so you want to correct for that before you stack. Then, so the final receiver function that you stack is basically the individual receiver function, the frequency domain. Then you can apply this time shift interface. Then once you do the inverse transform, you get your summation, which is the final stack of the receiver function. So just remind you that this is the geometry we are looking at. As you can see, we are going to look at all the response near the receiver, so in this case, near China. So here basically shows all the data we have for that constitute about 1,000 stations. As you can see, most of the stations that in the eastern part of China. There are some stations distributed in the west, but not a lot. And so we have basically about 1,000 stations, and so the total of the receiver function that we compute is about 100,000. And we, as I mentioned, we use the LQT system. So here shows where those conversion and the reflection sample. So as you can see, the red dots basically indicate the location of the pierce point, so where you actually sample the 410. And similarly, most of the sampling are in the east, so there is some sampling in the west. And after consider the SM ratio and also the correctness of the polarization, then you can basically stack all the quality receiver function together to make a nice image or nice stack receiver function. So I think this is the thing that I guess I really want to show. So typically, so I'm not sure if you look at this type of result before, but I think this is quite nice. And the reason is one, first you have a lot of trace. So in this case, typically a few thousands at different degrees. So in this case, we beam our receiver function over 1 degree distance between 30 degree and 90 degree. And so here, 0 time is the arrival time of the P wave. And as you can see, this is actually coming from the boundary cross and mantle, which is the mantle. And you have the multiple associated with the boundary at the mantle, so one positive, one negative. Then you can see this conversion, which is the exact predict by presence of the 410 discontinuities, and similarly for the 660. But what happened is because of this data quality and also the number of stacks, you can actually see this particular arrival, which is actually the top side reflection, and from the 410. And you can see the slowness also very consistent. So to see the SS reflections will be difficult because of the explanation is rather strong in upper mantle. So we still don't really see a good estimate. But still, this is actually good enough for us to make independent constraint on the density and the velocity. And as you can see, right, so not just this conversion that we were interested in, you actually can see the core reflection. So the P wave reflects from the combinal boundary, which is PCP. You can also actually see the PP wave that just traverses in the upper mantle, also the triple P. And the P wave bounces twice at the surface and record at the station. And you notice this frequency is up to 1 Hz. So if you really look at those pulses, they actually have some structure. So not just uniform, nice triangle. So in other words, there must be some up and down in terms of the discontinuity topography, or maybe the velocity is not homogeneous. But in any case, this is the fundamental data set that can be utilized. As you can see, this is done in 1 Hz. We can look at amplitude and their waveform at the different frequency band. So this shows another picture. So in this case, we up to about 5 seconds, so between 5 seconds and 40 seconds. So you see similar things. They are more coherent, of course, after filter. So here shows the conversion from 410, conversion from the 660. The top side reflection from 410, in this case, top side reflection from 660. So we basically have 2 pairs of observations for the 410 and 660. Then, as I mentioned earlier, you can easily retrieve almost any information that you want based upon these observations. And so, in other words, what we will do is do some broadband analysis at different frequency band, and you will see how the amplitude of those scattering wave, either conversion or reflection, that change as a function of the property at the 410 or 660. Again, right, so we can do this type of move out correction, so we can stack all the traces at different distance. So as you can see, so even individual beams that we can already see the signal, but it would be nice that we can basically collapse them into one trace. So it would be very robust over the area. So basically we do this similar analysis as just introduced earlier, and we can obtain this stack trace that over different distance. So in this case, we can focus on the conversion wave. So in that case, here is again the P wave at 0 time, and also you have this mantle at maybe about a few seconds after P. Then you have the 410 and 660. So of course, in this case, they are all corrected. So they are all move out corrected. And the final one on the right, so basically shows the estimate of our conversion at the 410 and 660. So in this case, this is focused on conversion at the 410, and you are able to give an estimate. And also, we can use the bootstrap method to give an estimate on the uncertainty. So this is useful. And then what we can do, of course, to do the different move out stacking, then we can get the topside reflection and basically give a final stack over area. One thing that I think maybe I want to focus is, as you may notice, I didn't actually stack over the entire range. Basically only stack over the range where it's free of interference from other wave. So for example, in this case, there are a PPP wave that transfers over this area, and also the PP wave. So to avoid interference, which is actually quite critical, then we only focus on this particular range where we don't have other waves to interfere. So now I want to basically look at other influence on the amplitude before we address our modeling in the neurophysics. And of course, as you can see, during the high frequency analysis, you can see a lot of little peak. Those little peaks are basically due to the discontinuity topography because they are not really flat. And also that will result in incoherent stacking. Here we can show a very simple example. So that imagine this is the distribution of the sampling by those conversion at the 410. So in other words, you can see the 410 go up and down. So in this case, between 400 and 430. What that means is when you actually consider this perturbation that introduce the amplitude incoherent stacking in your wavelet. So this basically shows at 3 seconds the incoherence due to the PPS wave, and also at the PS wave. So as you can see, the PS wave basically is a topside reflection, so it's influenced a lot more by the topography. So you can see the amplitude is quite low. In this case, the PS is much less effective. What you can do is basically to compute as a function of the period what's the correction factor for different phase. And we will use this particular correction factor to basically correct the perturbation. And one thing that I want to discuss is in this particular correction, the amplitude of focusing and defocusing is not taken into account. However, because we basically average over a large area, and those focusing and defocusing are much localized, and we assume that can be averaged out over the entire channel. And the second complexity is frequency dependent Q. So I think this is a little bit more complicated. So I think what I want to address is depends on the frequency band we are analyzing. So in this case, we focus on 1 second to 10 seconds. Here basically shows the T star, which means that the attenuation is strong with higher T star. And if you look at some of the measurement people done before using similar wave, so in this case the P wave, at higher seismic distance. So what happens is they see a lot of dispersion in the T star, which means the Q is frequency dependent. And if you look at some of the earlier analysis as well in the region, so in this case we use the SCS wave. So again, so this Q means inverse of attenuation. So in other words, the Q is actually bigger at higher frequency. So in other case, if you look at the amplitude, then you cannot use a constant Q. So in our analysis, when we take into account the amplitude that due to the discontinuity topography, we also take into account attenuation. So in other words, we consider the regional estimate of the Q at relatively long period, say about 10 seconds or so. Then we consider this observation that introduces frequency dependent Q with exponent alpha between 0.3 and 0.6. Then basically I give you some sort of a correction due to attenuation. Okay, so I think I have detailed enough about what we have been doing. And so I want to go back to the three questions that I started in the beginning. Right? So we said in the beginning we would like to see can we resolve this discussion between paralytic composition and the picogenic composition in the transition zone. And can we discuss the degree of vibration in the transition zone, in particular close to stagnant slab. Then, of course, we try to discuss what will be the consequence of mechanical mixing, whether we can observe any variable mixing stratification. So this shows the observation. So to start, the first question we want to answer, so if the mantle is parallite, then there's a prediction that can be realized. So we will basically use our observations to try to understand this discussion. So you can see, in this case, we show the amplitude as a function of frequency for the 410 conversion, and also for the 660 conversion. And also here shows the topside reflection at the 410, and also at the 60 as a function of frequency. So you look at the raw data, so which is the y squared without logography correction, and this is the observation of the function of frequency. As you can see, the amplitude becomes very small at high frequency. Once you take into account those topography, which causes the coherent stacking, then of course you recover the amplitude. And so in that case, this is the black. And I also show the prediction by paralytic composition, which is the straight line. So both for the 410 and for the 60s, and also for a different phase. So I think this, as a way to discuss or validate the composition, is very clear. It's so different, and so this space is different by about 50%. And if you look at this topside reflection, the same thing. It's basically too big by about 50%. And so you can also see there's some interesting behavior as a function of frequency. So if you look at the data, there's some frequency dependence, relatively weak. The observation has quite, but the synthetic and prediction by mineral physics has large frequency dependence. What does that mean? So that means when you look at the long period, there must be a large gradient that involved in the prediction. But in the data, actually, that gradient is not there. So it's actually, you can just look at the data you already know, and you can already guess what the model would look like. But if you look at the 660, and it's a different story. And the prediction, of course, at the long period is smaller than the data. The gradient that displayed by the data in terms of frequency dependent is actually stronger than the prediction in mineral physics. So I think this is quite interesting because it basically tells you something, at least in this particular locality, over thousands of kilometers square of area in China, you cannot really reconcile the prediction based upon parallel. And I think that's the key. So the gradient is too high at the 410, gradient too low at 660. And of course, in terms of the amplitude, they're not the same. So in other words, you can always use those observations to back up what would be a more reasonable estimate in the area. So I guess, at least in terms of this particular area, what we can say is maybe not. So near East China, so we do not think, based upon our analysis, the mantle transition zone is nearly paralytic. I think it's quite far away from paralytic composition. And also, second thing is the scale. So we mentioned about the mixing. So that mixing must have some scale. When we average over the entire China, as you can see, maybe about 15 degree by 15 degree, so it's quite large. What happened is maybe if we look at a smaller domain, the property may be different. So how does our averaging over entire China infer from a smaller estimate, reach estimate over a smaller area. But basically here we show two examples. So the conversion from the 410 and the 660. Here we basically show all the array that display in different color. So basically you can look at those estimates at this type of scale, which means a few hundred kilometers or so. As you can see, in some case, you can see large arrow bar because that they are associated with relatively smaller data set in that particular network. So they are quite different from the average over entire China. But otherwise, as you can see, there are some variations. This mean that we obtain over the entire China is meaningful. So in other words, there are some variation over different regime, but overall, this average we obtain over the entire China is a good estimate and a reasonable estimate. Then third, we mentioned about we want to discuss about hydration in the transition zone, and so that is closely related to the transition width. So here, basically, I show example by Frost 2008 between the pressure as well as the metal composition. So in this case, the magnesium number. So here it's free of iron, and here is 30% iron. So as we know already, so because typically in the mantle, we think maybe on average it's 10% of iron, so magnesium number of 90. And if you look at prediction for the dry olivine, it's about in this case 7 kilometers. So consider maybe you have some water in the transition zone, and the prediction actually suggests that the transition width is actually much broader, so maybe 50% broader than dry olivine. So as we mentioned before, so we have some tools that we can use. So in this case, as I mentioned before, the amplitude of those two different phases that really sensitive to the transition width, but in a different way. So basically, we look at the ratio between the two waves as a function of frequency. And if you look at a different estimate, so basically the black dotted line, dashed line shows the prediction of 1 kilometer transition. Purple line shows the 4 kilometer transition. And the same thing for the PS over the top side section at the 660. So as you can see, both results suggest the observation has indicate, in this case, very, very sharp transition. Doesn't matter it's 14 or 660. As you can see, the prediction for 4 kilometer transition is already over predict the amplitude at the high frequency. Similarly for the 660. So maybe, of course, it may not be a surprise that for 660 is quite sharp. But for the 410, depends on the water content, of course. As you can see over here, they can be 10, 20 kilometers or so in transition width. But what we actually see here is the transition width is quite sharp. Even sharper than a dry olivine with a magnesium number of 90. So if you consider a different possibility, that would indicate you move from 10 maybe to 5. So in that case, you are able to shop boundary as one possibility. So in any case, what we can say is definitely from this particular data set, the transition width is quite small and quite sharp. And so what we can actually discuss over the averaging over the entire China is this hydrated transition zone over a large scale. So in our case, we would suggest at least over the large scale, over thousands of kilometers. That may not be the case. And of course, we cannot exclude the possibility that there are localized hydration in some locality. But over large scale, we do not think that's the case. So as a calculation for the purpose of this study, so we can basically look at the transition width as a function of magnesium number. And so in this case, the solid line basically show transition width. So as you can see, if you move your magnesium number 90 to 95, you basically have a quite sharp transition, maybe about 3 kilometers. But one interesting thing is we know, or we think, typically from the modern analysis of metrology, mantle number is about 90. But if you look at those rocks in Archean, they have a much higher maximum number. So we basically entertain the possibility what we are looking at is mixing of more ancient components. So it's not necessarily modern Harzburgite. You can mix Archean Harzburgite, which can actually give you maybe a much sharper boundary. So the last thing that we want to discuss based upon this particular data set is the basalt stratification in the transition zone, which is one of the main focus. So now what we can play similar again, but in that case we can of course alter the basalt fraction as a function of depth. So in this case on the left, basically we show the amplitude for the 410 conversion reflection. On the right we show basically the conversion at 660 and the topside reflection at the 660. Their amplitude as a function of frequency. So this basically box shows the observation. So this blue line, the purple line shows the constant basalt fraction of 45%. So that's this line. Then if we allow the basalt fraction to change as a function of depth, so in this case, the basalt fraction actually increase toward shallower depths over some scale. So in that case, that scale is defined by h. Then we can do that, and then what you can actually easily observe is some interesting indication. So what happened is, so in that case, when there's a large increase with basalt as a function of depth, then this actually provides a much better match to the data. And so in that case, if you look at the red line, the basalt fraction actually increased from maybe about 40-45% to a lot more at relatively shallow depths within about 60 to 70 kilometers. And the same thing can apply for different phase. So this is for the topside reflection. So on the other hand, if you look at this large gradient display by the data, as we mentioned, the prediction from a constant basalt fraction do not really give you a large gradient, especially at a long period. And so what happened is we can basically do the same thing by decrease the basalt fraction as a function of depth. So in this case, h again is about 60 to 70 kilometers. And as you can see now, around maybe decrease from 35% to about 10% or so, that really give you this large gradient that is displayed by the data. And so this can also actually see that this is actually a consistent estimate for different variable. But you may wonder, so why I just perturb the basalt fraction above 410, and in this case below the 660? And the answer is actually quite simple. Maybe I lost a slide. But the point is, if you look at the velocity difference between basalt and Harzburgite at this particular depth, there are very large difference between the two above the 410. And the difference is quite small below the 410. So in this case, same thing. So there are large difference between basalt and Harzburgite below 660. Very small difference above the 660 in terms of their gradient. This is actually the reason why we don't have any sensitivity below or above the 660. So just to go back, so if you remember in the beginning, so this is the picture that in some coefficient dynamic calculation over a long time scale, and you can see it depends on the model. Sometimes they can, of course, look at this average 1D profile, then they could show some accumulation or increase of basalt fraction over the transition zone region. And of course, in this case, it's basically a short-term mixing. So of course, the indication of increasing basalt fraction toward shallower depth is a little bit difficult to understand, but maybe only one possibility is that they are transient estimates. So they do not represent a long-term result of long-term mixing and rather than short-term mixing. So of course, we can go back to this picture. So now as you remember, so basically this C2 is pretty much what we are seeing, except we have some much larger basalt fraction towards shallower depths. So if you consider these two different possibilities, and what we would think is this is probably more consistent, at least in the area in China. And of course, if you think, at least according to this particular study, that sample area near China, close to the stagnant slab, if you do have a much more basalt than you expected from a prolific composition in the transition zone, they also affect other observables. So in this case, we can look at electric conductivity. And here basically shows a few measurements and model that in the same region, including sea and also northeast China. So from 100 kilometer to about 650. So as you can see, the electric conductivity increase with steps across the transition zone. And of course, here shows the prediction by Corrado and Yoshino. Of course, a different model that gives a different estimate in terms of the electric conductivity. And of course, typically, depends on which model you choose, the estimate on the water content is a little bit different. But typically, maybe around 0.1 to 1%. But I want to stress that if you consider this basalt accumulation is a reasonable estimate in this area, what happened is if you look at the Yoshino 2008 estimate, so this basically shows the observation in northeast China. This shows the estimate of the electric conductivity for more at transition zone depths. So as you can see, this high electric conductivity from the more is actually a different a possibility that people do not really entertain very much. But to be consistent with our estimate from seismology, we think maybe some of the high electric conductivity can be attributed to accumulation of more intertransition depths. So we just display a few summary, and of course we use the broadband data to try to offer a good, consistent way to elaborate detailed picture. And we give a very small number over China. In this case, about 1.5 to 2% density jump, which is very low compared with Pillay composition, which is about 3.6. And we give a very sharp 14 and 660, and typically below 4 kilometers. And regardless whether the mantle is dry or wet, we seem to require a much higher magnitude number, probably larger than 93. And of course, one thing we can ask whether we are missing something, because we primarily focusing on the modern archeolite, modern basalt. What's the property of Archean archeolite? What's the property of Archean basalt at transition depths? I think not a lot of people try to calculate, but it will be interesting to see. Then the last point I want to say, of course, the gradient is consistent with the basalt pressure very substantially over the transition zone. And this could be, of course, constant for short term or long term mixing. And there are, of course, other implications that you may draw from here. I guess I will stop here.
Thank you very much, Alex. Do you have any questions for Alex? I'll start one. So that question about the magnesium number being greater than 93, could you turn it on its head and say that if we think we've got a better constraint on the magnesium number, is it telling us something's wrong in Hephaestus or something in the way of parameterizations?
So I think in terms of Hephaestus, that if you look at the different analysis, Hephaestus give a consistent estimate if you make a consistent magnitude number. Say, for example, the calculation was done for magnitude number of 90, which is typical. Then if you consider that calculation, that gives you about 7-8 kilometer transition width, which is pretty much the same as all other analysis. So we probably do not think that that's the reason. And actually, we think that a highly magnitude number is consistent with what we think to shock the transition width. And of course, there are different possibilities.
Yeah, what's the alternatives instead of saying it's this?
Yeah, so of course, some people look at the refer through the transition seismic discontinuity, you result in some equilibrium which actually result in a much sharp boundary. So of course this could be the possibility, but I find it's relatively difficult to explain. Why, if that's the case, why don't we see all the observations that invoke sharp boundary? Because that's the response dynamic wave. We sometimes see a sharp boundary, sometimes see a smooth boundary. So that cannot be the result of just dynamic equilibrium. And of course, there are some other possibilities, so I haven't maybe touched upon. So I guess, as I mentioned, so we emphasize this is a nice data set, we have a nice observation. And regarding which direction you prefer to approach to resolve the difference between prediction and observation, there are, of course, a few possibilities. So I mentioned about this Archean Arthmogite, also Archean basalt. So actually, we calculate a little bit, and the result is quite surprising, but also quite interesting. So what you see here is the RSP, so that's the dash line. You also see the parallax in blue, so that's this one. You see the calculation for the modern basalt, so that's the red line. You see the calculation for the Archean basalt, which is this one. So you can actually see the basalt itself in this particular case, because the increase in MgO, so the albumin is stabilized in basalt. So actually, just by basalt itself, you can give the sharp boundary, which is not happening when you look at the modern basalt, because basically the albumin is not stable at that depth. And you can also see a second feature from this Archean basalt is below the 660, you also invoke a very large gradient, which is basically what we seen with a large gradient. So, of course, in our case, we attribute to the depth dependence of the basalt fraction in our model. But if you just look at this particular calculation on Archean basalt, it has many interesting features that we didn't explore. So that's why I mentioned that there are, of course, different ways you can explain the data, but one thing is, it's very hard to be consistent with probability computation. At least if you consider a mixing model, then you need a lot more salt than that's always the case. And maybe second thing is probably this one. So as mentioned, so if you look at the transition width, so this of course is quite large, right? But this is at 0.4 weight percent H2O. So depends on what we think about the water saturation in the transition zone. So if it's saturated, then it is possible to be sharp. So if it's in the middle, then it can't. So I think maybe that's another possibility.
Do you have any further questions? In which case, can we thank Alex once again, and we'll go for some tea. Right.
Thank you very much.